Hello everyone to this webinar, Australia Journey to Net Zero, and I'm Yogendra from EA Technology Australia, and with me my colleague from EA Technology UK, David Mills. So we will be sharing you some insights, and especially those insights, how they can be translated into the Australian background. Look, I've been in the electrical network industry or electricity industry for some time, and there was a time when we were thinking there's nothing exciting, new, creative happening to the industry. People used to tell me that this is becoming a dinosaur, same transformers, same poles and wires. What is there? And look, I can see now that it is so much exciting stuff is happening. It is transforming. It is all the new and creative things are being talked about. So this is the most exciting time, probably once in century kind of thing, I can say, which we are all going through.
As you said, I'm David Mills from the UK. I'm here to share some of our knowledge and work that we've been doing over in the UK. Just wait a couple of minutes for everyone to get connected.
We are seeing people just joining just now, so just give us 1 or 2 minutes and then we should be good to go. So this is, let's start. I just wanted to put this last draft scenarios with AEMO is doing a great job, especially the ISP, the kind of efforts that have gone, it is fabulous. Now we can see that all these scenarios, so let's say what was put in 2021 and step change is one of the central scenarios. Now this is a draft, so this is not the final one, but I'm just showing it here just to demonstrate that how these central scenarios are coming closer. So this is becoming narrower. That means that we are about on a journey which is certain to happen. So the only difference I could see is that step change is still there, but between the step change and progressive change, there's another one they are thinking that might be another scenario for the time being. All these scenarios depend basically on 3 things. One is the economy, how it is going up and down, the electrification, and then DER uptake. And all these are also not mutually exclusive. So what we are seeing is, or AEMO is seeing a slight shift from 21 to 23, and this is in Australia. Again, emphasizing, I'll not go through all the points, but suffice to say that in the exploring alternatives, which they are saying, so either it can be central scenario as exploring alternatives or a step change for the short term. The difference is that whether Australia sees, the value in the green gas and the cost effectiveness in the green gas, and that it slows down the electrification. And the DER uptake, whether it happens moderate or it really happens, much more. So that's the key difference between the step change and the exploring alternatives. The step change is saying that electrification will happen more rather than green gas is doing something in between, and there will be much more uptake of DERs, especially the EVs. I mean, Australia has already done and on the journey for rooftop solar, so that is unstoppable. It's only a question of how the EV uptake happens in this part of the world. Now, this is another thing which I wanted to just share, because this will set the scene. What is happening? Like, say, for example, last week in Western Australia, we had seen that 2/3 of the demand was met by the distributed generation, and so the minimum demand on the system actually became very, very low. I mean, it is a good thing. We should be celebrating, in a way. But yes, this does pose, the challenges for the system operator. How do they manage, the system strength and reliability and the frequency control? So this is something is happening in Australia, and this is also indicative of that Australia is a land of opportunity where we have got so much rooftop for the solar, we have got off-street parking, we have got so much land where we have the resources like sun and wind. So, and this is all coming to now to actually give this kind of effect, which we are saying. Yes, there are some challenges, but those challenges are not like they can be managed. Once we know about them, this can be technically managed, but this is what is happening at the moment. Now, the ENA has actually issued the energy vision recently, this year itself. So basically, the ENA is also trying to say that pathway for net zero is emerging, but whatever happens, the networks will have an important role to play in those pathways to facilitate those pathways. And this is from the ENA net zero, how we will deliver. So one thing is very clear, that mandate to decarbonize is there. It is now the question is, how do we manage the risk, investment risk, of too early or too late? So all these scenarios, all these no regret actions, the least regret cost, the net market benefits, everything which has been talked about and has been worked about is that we actually minimize or optimize the risk of too early investment or too late investment. I'm not going to detail this, but these are kind of future use scenarios which ENA has put up, and they are all valid, and this is already happening at a household level, the transport level, the community level, the industrial processes. They are also, especially the heat, the export thing, energy export, and the hydrogen. All these things are happening in Australia in some way or form, and as we are saying, the scenarios are also becoming narrower, which is showing that there is a definite pathway coming up. And now I'll ask David to take over from here.
Thank you, Yogendra, and morning, everyone. So I've come here to talk about some of the work that we've been doing in the UK, and try and give an oversight of how some of the distribution networks and generally energy industry in the UK is helping to prepare for net zero. Some of the biggest changes that we are seeing in the UK, we've had a growth in flexibility markets, as more and more trials are taking place, so we're encouraging systems where demand and generation at distribution level can provide flexibility, and last year we had nearly 3 gigawatts of flexibility services tendered. We're also a huge increase in LV connection tools. So that's due to all the increase in DER connections. So it's helping the networks to be able to process those quickly and automatically, so that customers can apply for connections. And a big driver in accommodating all these new technologies is how do we ensure that it's fair for all. So at the moment, if you can afford technologies or afford connections, you're at an advantage. So looking at how you can work as an industry to make it fair and reliable energy supply that's also cheap or cost effective for all. And the biggest challenge that we're now looking at facing in the UK is dealing with our low carbon heating. It's a bit cooler, and trying to shift away from the gas system. So our distribution networks in the UK have an innovation fund that they're allowed to spend on various areas, and during ED2, which is our next regulatory period that comes into effect from 2023, these are some of the areas that they're focusing on. So the key themes being about understanding more about what's going on the network, and also how do you make it easier and cost effective for new customers to connect to the system and increase our uptake of low carbon technologies. And that's all links back into that requirement around flexibility, being able to shift demand to align with when there's renewable generation available. but whilst doing that to avoid excessive bill costs or connection costs. And so this graph at the bottom shows for each of the different distribution networks, color coded there, where they're focusing their expenditure during ED2. You see the biggest drive is how to get more technologies connected to the system without having to constantly invest in network enforcement. And part of that, of course, is getting them done quickly, making sure that we actually get the infrastructure in place. So that leads us to a project that we've recently delivered for the UK government, for Department of Energy, effectively wanting to know what are the options available to them to actually accelerate this uptake of technologies, get more connected to the system. So some background. Obviously, we all know electricity demand is increasing. We're trying to shift to electric vehicles, low carbon technologies. It's all moving away from fossil fuel sources. So here's some sort of stats that we're seeing as part of our forecast in the UK. So we're estimating, we're already seeing a massive increase in electric vehicles, particularly fully battery electric. It's only expected to increase over the next up to 2050, with some legislation changes coming in the next 5 to 10 years to accelerate that. So one electric vehicle is estimated at 3,500 kilowatt hours a year, and yet a 3-bed terraced house that we have in the UK typically averages 3,000 kilowatt hours a year. So you can see it. If each house is having 1 or 2 electric vehicles, we're going to see huge changes in energy demand. Start looking at the peak demand. So typical EV charger at 7.2 kilowatts is peak demand in the UK, and yeah, our kettles are running 3 kilowatts. So we've got both huge amounts more energy to get down the existing network, but also dealing with those peaks as well. But that's just one side of the problem. We've got all this decarbonising of heat taking place, growth in heat pumps, and so you can see some of the demand we're looking at there. So we've got 3,000 kilowatt hours for the house again, and then we're looking at 5,000 kilowatt hours a year for space heat. And obviously that peak demand, so 4 kilowatt peak. Obviously, not everyone's going full wax, so some of the analysis we've shown has diversified those peaks. So you can see there's all huge amounts more energy that we need to get down our system. This is a future energy scenarios produced by National Grid, the system operator. And on the left there, we have our 2020 total energy demand, and then the scenarios on the right. So the green scenario being the only one that actually achieves the net zero 2050 that we're targeting, but that's forecasting nearly a doubling of annual consumption. And then we look at the peak demand. So we're current peak demand in Great Britain is around 60 gigawatts. Electric vehicles are forecast to add between 10 to 15 gigawatts of more demand, and obviously heat pumps, you can look at that as being an extra 10 to 25 gigawatts. So huge increase in peak demand and huge increase in total energy consumption. Now, obviously, the standard solution is we just go and upgrade the network. So we look at putting in new cables, new transformers. Now, not only does that cost a lot of money, but it takes a lot of time. So we're looking at trying to fit that all in. And you're looking at these some of the costs associated with this installation in the UK, just typical costs. So for every new substation, every new transformer, every new cable, this is the counterfactual that the networks are using as their basis. Now, that's all going to cost a lot of money, going to take a lot of time, and isn't achievable within the time frame available. So the Department of Energy wanted to know what are some of the alternative options that could be considered, how else could a networks work together. So they came to us, or we carried out some analysis using a transform model. This is a modelling tool that we've developed in the UK, we used in Northern Ireland, some parts of Australia and New Zealand as well. Effectively allows parametric representation of the network, and we use this to estimate the requirements of the future grids and consider where conventional solutions, so there's new transformers and cables, work, but also where there's new smart solutions. So what are the emerging solutions that could be used instead of just replacing the assets? How would they work? Would they actually save money over the long term? So to start this, we had to figure out what is the scale of the problem. So we initial analysis using just the technologies that are available at the moment suggested that it would cost £65 billion to invest in just the LV network between now and 2050. And that's just for new capacity. We then went away and looked at what are the new emerging technologies that are beginning to appear on the system, and I'll go into a bit more detail what those were in a minute, and how would they help relieve constraints on the system or operate the network more efficiently. And to do that, we had to quantify what difference the new solutions make, what's most important, and how do we get there? What are the barriers and challenges to getting these things onto the system? So to do this analysis, we needed to know what the demand scenarios were, which I mentioned earlier. So we were able to capture those in the network modeling, understand what the barriers were. And what were the parameters? So when does a distribution network become overloaded? Is it a voltage issue or a thermal issue or a power quality issue? What types of different network are there? Are they rural, urban, somewhere in between, long feeders, etc.? We modeled all that in the system. And then what are the available solutions? So we obviously have the transformers and cables, and they all have costs associated with them, both in terms of capital and ongoing maintenance. But then we've got these new solutions, which are emerging technologies, and we have to estimate the costs and deployment of those. So to start with, just to bring back what is the cost without these solutions? So we carried out an initial analysis. This showed that if you just used conventional or solutions which are currently being deployed on the network, that generally is new transformers, but there are some other solutions part of that. We're looking at £65 billion in network investment. Small amount of that spent by 2030, and then a huge chunk between 2030 and 2040. So that gives us the kind of both total amount, but also how long we've got to get the systems moving, get new solutions on the network that can help to more efficiently make use of the existing infrastructure. So in that analysis, we quantified where the majority of that money is spent. So this is the average number of these upgrades or solutions needed per year, and the majority of that is effectively splitting the existing feeders or adding in new circuits from existing transformers as well as new transformers. Now this is obviously per year, assuming that we can deliver these levels of infrastructure investment. So obviously as the system evolves, we've got new problems. Electric vehicles, huge demand, peaky demand, and different operational challenges. But they also bring new solutions. So some of this analysis focused on what are these new solutions. So we have network size solutions. So this was looking at where the new technology is coming out, so where we have ability to do dynamic meshing of networks on the LV side, new transformers technologies that can help more optimize the voltages on the system better. We also have customer side solutions. So what are the flexibility options for customers that can help to actually manage the network demand better, avoid these peaks or shift demand to times when we can manage it better. And then of course, policy solutions. Are there any policies that can be changed that would allow the networks to operate within their constraint boundaries more easily in certain situations? What would be the knock-on effect of this? What else needs to be considered? So we captured all of this in our modeling tool. For each solution, we have a capital cost, operational cost, but also what's the disruption to the network, disruption to the customers, when are these solutions available, what's their lifetime, where else, how might their costs change over time. So we've got emerging technologies, we might actually make it get cheaper. So how much is it going to cost with all these solutions? This is the question that we were aiming to answer. So as I said before, without any of these new solutions, which are emerging technologies being tested on the network, we were looking at around £65 billion. Once we've deployed these new solutions, we estimated that the cost saving could be nearly 35 billion. So nearly halving the cost of investment just as a result of being able to get these new technologies onto the system. Obviously, that's not a simple process. That's what the department, the government wanted to understand, and how they could help work with the regulator and the networks to encourage this. So which ones are most promising? So I've highlighted here the solutions that we used previously, and it's obviously we're still going to have to replace our transformers. We're still going to have to put in new cables and new overhead lines, just in much smaller quantities. We're getting better use of our existing assets, making more efficient use of them. You can also see there's a significantly greater number of deployments here in total. Small technologies available being used in different areas. So as we work through, you can see there's active transformer cooling, one of the solutions, the introduction of demand side response and providing control of these devices, and obviously meshing the LB networks. So some of these are still asset-based solutions, but they're solutions which aren't currently deployed readily on the system. But we had three particular solutions that were outliers in terms of how effective they would be at reducing these costs and making the networks more efficient. The first of those was network data monitoring. This is not strictly a technical solution that helps to release any capacity, but means that we know how much spare capacity there is on the system. Once we start putting monitoring on the LB networks, we then have more information about transformer loading. We can do fault prediction. We can also look at enhancing the ratings of transformers because we know what the load profile actually looks like rather than just how it's assumed. The next one was manual phase balancing. So we're looking at obviously new electric vehicles coming off the system. There's huge demand on the network, but not necessarily equally across all phases. So there's a significant effort required to actually balance the phases better, whether that's manually going out there or with improved automatic systems, which are still emerging. In terms of doing that, you then have to improve your modeling to start with. So that's where your network data monitoring and helps to understand which phases are poorly loaded or heavily loaded. But an outright winner was around the idea of behind the meter domestic battery storage. We're starting to see this emerging in the UK, and it's a solution which provides huge benefits to the networks. If you can create the correct tariffs or financial incentives, you can get customers to shift their demand or charge batteries and use them as self-supply. Now it's obviously been talked about for a while. It's growing in popularity, and it's just encouraging that uptake. That's the challenge. Now, when we presented this originally, we get we're talking about 25,000 battery deployments per year, which is a huge number to get across the country. and it's a bit far-fetched. You know, how are we actually going to achieve that? Are we going to expect customers to start purchasing these batteries on this expectation they can make a return? Well, we'd argue that some people are already looking at that. Once you start getting an electric vehicle and you're charging that, you've already effectively created a battery storage device. Whether that's just through demand control and charging, or whether you look at solutions like vehicle to grid, doesn't directly matter in terms of how that can help manage the network. And obviously, we've got big uptake in electric vehicles. We've got evolving tariff structures and control systems as part of those flexibility trials in the UK. And we've done a lot of research in that area, looking at how you can get customers to shift their demand behavior and how that helps the networks. So what next? So we've been working, obviously, with this, provided these recommendations to the UK government, and they want to know how to take that forward. So around network monitoring, obviously we've got an ongoing smart meter rollout program in the UK. It's up to 50% now of properties are on to smart meters and accelerating uptake. But that doesn't tell you the whole story. That just gets you down to the customer level when you can get access to the information. So there's still a need for actual LV feeder monitoring, the LV outgoing circuits, understanding how the loading is, what the transformer loading looks like. And so we're providing solutions that help with that, along with a lot of data analysis work to, you know, how can you improve the ratings of transformers? How can you help with fault prediction and keep the system more operational? There's a whole number of other benefits. And then there's challenges that the government's working on. So behind the meter energy storage, it's not trivial. You know, it's expensive, whether you're looking at combining solar with batteries or even electric vehicles. They're currently still expensive to get installed, and therefore only suitable to those that can afford it. So there's a lot of effort looking at how we can help people who are fuel poor or struggle with some of those costs to make it fairer access to the network. And in all about locations where it's not possible. So trying to establish systems that mean that you can share some of the benefits across local areas, create local markets. Which moves on to shift, looking at effectively street level flexibility markets. All the markets in the UK at the moment are quite wholesale market priced or based on very large areas by the distribution networks. To overcome that, we need to shift down to looking at local street level flexibility, and this is where the behind the meter storage can offer a benefit. But it's also got to be simple and easy to understand. Everything that we see in the UK at the moment, I'd say targets those that are interested and early adopters, and doesn't pass some of the simplicity tests that we need to actually get wide-scale adoption. So there's a lot of focus going on how to make these tariffs and service models simpler to understand. And then, of course, smart EV charging. So we've delivered loads of projects in the UK looking at how you can incentivize customers through time of use tariffs, through direct control of charging, whether that's at domestic individual customers, through fleets, or through aggregators. We've just had regulations changed in the UK, so we now have a requirement for all smart charging points. So any new EV charger that goes in has to operate off-peak tariffs only and be controllable. Those are starting to roll out. That became a requirement as of June this year. So that gives you an overview of some of the work that we have been doing in the UK, helping to accelerate the net zero transition and help the networks and the government understand how to increase the uptake of low carbon technologies. And we're obviously working with networks and local authorities to stimulate this. I'll now hand it back to Yogendra, who will talk about how some of this applies directly to the Australian market.
Before you give it to me, someone asked me that question, and probably you can answer that. Is how much of that the information you presented is in public domain?
Sure. So all of those The results I presented there are public on the UK government website. It's been a published report that fed into the network strategy transformation document, and we can circulate a link to all of those publications after the.
So how good it is? The UK has already done the policy decision that all the EV charges will be smart charges going forward. I mean, this sort of thing, like maybe a good thing for us also to consider in Australia, because why to have the same policy after 2 years when there's a lot of dump charges are installed? Why? So we probably, well, this is a kind of thing which got my attention. Is that fantastic? Like all the EV chargers should be smart chargers anyway. All right. After that thought, I'm just giving one example what we have done recently. EA Technology has done this sort of thing with other networks, but this is the recently we have done with one of the Australia's DNSP, and basically just demonstrating that this sort of thing, how it is helping not only the regulatory submission but also in our journey to net zero transition. So for this particular DNSP, what we did is we did the hosting capacity. And yes, most of the DNSPs in Australia do not have the LV model ready. So this is done on representative, feeders or characteristic characterizing the network, taken from taxonomy or anywhere, whatever the best representation of the network, and saying where is the hosting capacity, where is the issue of voltage and thermal, and that kind of, and this required the modeling. So this was done, and once that, after the modeling on the prototypical feeders, the hosting capacity was determined, and then the next task was to use the transform model, which is a parametric model developed by EA Technology. So to investigate, saying what are the solutions and what are the costs of that, and then testing the alternative strategies and saying what is the investment looks like from now to 2050 and what is the best strategy. So this work had just been completed for one DNSP here, and this again I'm saying this we draw upon the lot of information from the scenarios and also the DER uptake from the AEMO's ISP, which is published, and in particular that geography. We are seeing what are the trends and what are the scenarios. What solutions will work and what will be the investment cost going up to from now to 2050. Just an example that what was delivered as an outcome is that different kind of feeders on the vertical axis and saying on the horizontal axis saying this is the kilowatt per customer you can allow if everyone has the solar on their rooftop, and different kind of feeders will have different threshold for how much solar can be allowed, or the net export here. It's saying that this particular route saying the net export it is doing to the grid before the voltage becomes an issue. Of course, there is now the new standards with AS 4777, which have better volt controls, but they are just coming in the mix. So most of our rooftop solars do not have that kind of capabilities. But with seeing these kind of static limits, this is not dynamic, but this is saying this is a rough guide and saying this kind of limits will apply on this particular types. Moving on to another one, which the part of that another outcome from that study using the transform model was saying, okay, under different scenarios, let's say for electric vehicles, and we say how many people go on time of use tariff. And time of use tariff, is like minimum or medium or high, uptake, and then how the investment will change under those conditions. So this is just to give an example what kind of studies we can do and find out what is best for that network, for that geography. Some of the conclusions, there are a lot of conclusions, just I wanted to draw upon one or two just to give you an example of these sort of studies. Is saying we can actually use the volt var control, and it can absorb VARs, it can control the network voltage, but at the same time it will increase losses. The voltage control with the tap changing, lowering the tap, that is also possible. So there has to be many other ways to manage that voltage issue, and similarly to manage the thermal issue when it comes later because of the EVs. Now, in terms of the EVs, we saw that time of use and demand side management both are attractive. Saying either we actually encourage the customer behavior because of the time of use tariff, or we actually do the load control or manage EV charging with the demand side participation, and both will work. And then we go to how much is more optimum, and in that we saw that even if we get to median like 50 to 60% people are on time of use tariff, that should be enough to give. Beyond that, it doesn't give necessarily the economic benefit. In fact, it might create another peak and maybe some downside with that. And similarly, demand side management, we don't need 100% people to participate in those managed EV charging events. And our finding was, even if the 50% people are available, for these things, both for absorbing solar in the daytime, so soaking solar in the daytime, and also to manage the peak demand, shifting, curtailing the load when the network peak demand is there. It helps the network optimally. So these kind of strategies under different scenarios we can test, to find out what is the best or optimum spend. So again, I'm coming to the same point. The question is, what is the optimum spend for the network, and how to de-risk spending too early or too late? So I think that's from me, and David, you can join now for any question answers.
Thank you. And I think, as I said, put up here, so we're heading to the EA conference in next week. So if anyone who's there, you'll find us on booth 50. We'll be happy to discuss anything about the work we do. And I will be giving two presentations. 20th and 21st September. First one, looking again at some of the work we've been doing to help understand how new technologies can help improve LV network hosting capacity. And then the second project looking at smart local energy systems. So some of the work that we've been doing with local authorities, aiming to help understand where you can locally match demand and generation, how they can accelerate within a local region on their journey to net zero, with a lot of, particularly in some of the areas of the UK where they're focusing on achieving that very quickly. So happy to take any questions. If you've got any questions, feel free to chat. We can take a couple of them now. So there's a question here on around determining export limits in Australia. So effectively wanting to understand what the biggest challenge is, whether it's a voltage issue or thermal issue. So from the analysis that we've carried out, it depended on a particular region. So some areas where they're seeing very high PV uptake, typically would be hitting voltage issues first. So that's along the feeder. But there are other areas where actually it's electric vehicle uptake that becomes a challenging issue. So you're now more into typically a thermal challenge. And obviously the biggest issue that the network has is you're studying for one situation where where you've got huge demand and voltage drop along the feeder, and yet the circuits very nearby potentially have a huge PV. So you've got this separation there in terms of whether you're managing voltage effectively locally, you're trying to keep voltages low, and then you're also trying to keep voltages high. So the shift in looking at volt via response is helping to improve that. We've modeled that to show that you can now help to balance that voltage locally, so you stay within limits, and therefore you can get more PV generation of the system. The challenge is that's a recent change, and it's going to take a while for that to propagate into the network. So when issues are already being hit, there needs to be some alternative solutions. So I've got another question here looking at the role of intelligent algorithms in EV uptake. So I'm not entirely sure what you mean by intelligent algorithms with regards to EV uptake, but in terms of running charging control, we see a number of different solutions. So that some of it is direct control of EV charge points, some of it is through suppliers and aggregators. So we're setting effectively providing objectives to aggregators to limit the amount of charging they have across several vehicles or several hundreds of vehicles to help balance the network constraints. We're also seeing new kind of connection agreements emerging where customers are allowed effectively to control their own demand within a threshold and they get a cheaper connection as a result of doing that. I'm not sure, Yogendra, if you have anything in terms of EV uptake in the UK. Sorry, in Australia, any way that that's taken forward?
I mean, Australia is still not that much EV uptake, so we are not seeing that thermal issue and the peak demand. And there have been in Australia at least 2 or 3 trials of managed EV charging, including the EV grid. So we actually attended this deep dive session, which was encouraging. Interesting point is that although there are early adopters, but there are people who are actually behaving. The customer behavior is very encouraging, especially from the residential customers, saying with the time of use tariff and even without for some response, they are actually agreeable to this managed charging. At least the customer is not saying, why do you manage my charge? The customers are cooperating in the managed EV charging, which is in Australia. But time will say, when the mass adoption happens, how that kind of customer behavior and preferences come.
Yeah, there's always a challenge there with early adopters and more engaged. There's another question here looking at difference between using representative networks versus real networks. So obviously, if you have real network data, we can carry out far more accurate and granular analysis. In the UK, we've done some analysis of that. We've got simulation tools that let us, when we have full connectivity models, model different DER uptake scenarios, look at solutions, and understand how they will help to resolve the network constraints. The challenge we have is a lot of the distribution networks haven't got those LV connectivity models available. So once you get down below the HV networks, there's nothing to do. So that's why we're looking at representative networks. It's also for the purpose of providing kind of whole system advice to regulatory and the government. They just need that big picture. We certainly are nowhere near having a complete GB-wide power system network model yet, but it is being worked on.
I want to add to David is, look, don't lose your heart. If you don't have full LV net model, that's okay, because we don't actually, if we can characterize and model the prototypical feeders and have some monitoring on to validate those models, they are reasonably fit for purpose. So it is actually, and then so it is basically, either you invest too much on having the full model, and which will also to be kept up to date with all the DERs coming and all the changes coming in the LV network. That is one side if somebody can do it, but otherwise, having the modeling and some monitoring will give us fit for purpose, quite reliable, predictive models with confidence, which we can say. And then when it comes to the few areas where there is an issue, yes, then that can be done in more details. So it is better to actually model those LV areas where we see an issue or risk of voltage or thermal constraints, rather than actually spending too much money and having to wait for a longer time to have full LV visibility and then start action. That is my view.
Yeah, certainly, and there's a big push in the UK for LV monitoring on the worst affected transformers, so we can understand how we can get a bit more life out of those transformers. We can look at changes in the load profile and how they're going to impact the rating, and particularly forecast when those transformers need to be replaced as we have more low carbon technologies connected to the system. It's the distribution networks want to know is that these transformers in 2 years, 5 years, 10 years, where can we help with that analysis? So I think if there's any more questions, if you have any further questions, feel free to reach out to us. Contact details are on the slides there. And after the webinar, we will send around copies of the slides and also some links to where some of the material that we've talked about has been published openly to discuss or provide further information where that would be useful.
And David, what this QR code is for?
So the QR codes are there just for anyone that has wants to, they can just scan that and that will send you a link directly to our contact details. So you have to quickly type them in, but that'll be circulated afterwards. I don't think there's any further questions. Obviously, we will send around links to the where this material is public, and apologies to anyone that had challenges with the audio. Certainly, if you want any further information, do contact us, and we'll happily share some learnings that we have from projects delivered elsewhere.
And thank you everyone for joining this morning and actually asking the good questions. And thank you all. Thank you very much.